Welcome everyone. In the previous session we talked about the phase detectors and we discussed analog and digital phase error detectors. So, just a brief recap. So, we looked at phase detectors and there were analog and digital kind of phase error detectors. You have seen two of them as analog and the other two as digital. This is mixer based or sample and hold based, and the other one which you looked at was your exclusive OR gate based PD and SR latch based PD, okay, as a flip flop based PD. So, with both these all these phase error detectors, we actually measured the phase error between the input and the output signals, right. Now, when you are using these phase error detectors in a PLL, right, you have to detect the phase and frequency both. So, in that particular case, whether you have the phase and when you have phase and frequency both, we need to check whether these phase error detectors will be able to detect the frequency error, okay, or for that matter even the whether the frequency error which it can detect is large or small. So, those things we need to check. So, just consider the phase error detector PD, either of these you will look at both of them, all of them actually. You have R and V signal, and what we used to get is VPD, whether VPD we are getting after subtraction between the up and down signals in case of SR based PD or the digital one where you have exclusive OR gate PD. Okay, so, the phase error detector output which we plotted was VPD average versus phase error, and this is something which we have seen that there were sinusoidal phase error detectors which we saw. Okay. Then there were the one which we saw earlier was XOR based, where you have your output going like this. Okay, so this is pi by 2, this is pi. So, you had the XOR based PD, and you have also seen SR latch based PD, which was something like this. Okay. So, for all these phase error detectors, let us look at the interesting part about them is where we are looking at whether they can detect the frequency error or not. Now, consider these two signals R and V and assume that FR is not equal to FV. The two frequencies are not same. If it is sinusoidal, then you have seen if the two frequencies are not same, the phase error will keep on increasing. Okay. If you are just looking at the phase error detector alone, then the frequency, then the phase error will keep on increasing. If it is in a closed loop, then based on the loop operation, you will recover the frequency. But here we are looking at whether we can detect the frequency error by using the phase detectors. So, in this particular case, as we write, so if FR is not equal to FV, your phase error will keep on increasing for sinusoidal signals, which you have seen. In case of sinusoidal, phi error of t is 2 pi times FR minus FV integral dt. That is what you have for sinusoidals. Okay. So, what is going to happen for the phase error detector? If you give a sinusoidal signals, the phase error keeps on increasing in this direction, okay, and VPD output which you are looking at over a period of time, you will see the VPD output has the sinusoidal waveform. Now, what's so important about the sinusoidal waveform? If you look at VPD, which is varying in the manner I have shown, then the average value of VPD is equal to 0. Okay. So, for a standalone phase detector, if you have a frequency error at the input, the average value of the phase detector output over a given period of time is going to be 0, and which makes sense also by just looking at the plot, that what you see here is you are having equal the average value of VPD as phase error keeps on increasing. You see from the top and bottom curves, the area under the curve is equal to 0. Similarly, what is going to happen when you have a square wave? So, just let us take a look at here. So, you have, let us say, SR flip flop based, right, and this is R signal, and then I have V signal, maybe it can start with the same point, but you can have this as a V signal. So, you will detect phase error. There is a very clear frequency error which you can see with respect to V signal, right. So, first cycle you see there is no error. Second cycle you see the error between these two edges. Third cycle you are going to see error. Third, this and this both are actually going to give you down signal, and then you see error with respect to this. So, 1 this is continued, and then you see lot of error with this. So, this error will keep on increasing, and depending on the frequencies, what you will see is, for example, if FR and FV they are different frequencies, then whatever ratio they have, FR over FV, just for example I am writing that ratio as M over N, right. It implies that N times your TV is equal to M times TR, where TR and TV are clock periods for R and V signal. Period of R signal and period of V signal. Okay. So, by writing this by writing this ratio FR over FP as M over N, what I have told you here is that N times TV period is equal to M times TR period, and after that this is going to repeat. And when you see this over N times TV period or M times TR period, you will see that you are actually spanning the whole curve. You will actually span this whole curve over a given period of time. That time is equal to N times TV or M times T error. So, as the phase error keeps on increasing, VPD also keeps on changing, and when you take the average of VPD over a given period of time, what you will see that average is equal to 0. So, it will not be able to detect large frequency error in any case, even if sometimes the frequency error may even be of the opposite sign. Okay. So, the problem here is, so first just understand this particular part, that because I have been using phase error detectors in the previous simple PLLs, where I used to also recover the frequency error whichever we had, but here now I am saying the same phase error detector is not able to detect large frequency error. Okay. So, you may see an ambiguity, but let me clear that. So, previously in the PLL where we use the phase error detector, PD and loop filter, right, with VCO. The loop filter was type 2 loop filter and so on. Type 2, the PLL was type 2 PLL, and in this particular case, or the assumption we had, that initially we had the frequency error. Based on the frequency error, we will get VPD, and this VPD gives you control VPD output voltage, which gets filtered by control voltage, and you recover the frequency error. So, we have seen multiple cases where your phase error exceeds 2 pi, then also you recover, or your phase error does not exceed 2 pi, and then also you recover, right. So, all those things were happening in the closed loop. Okay. In the closed loop, if you have loop filter with an integrator, you were able to do so, but standalone, if you look at the PD, average value of this PD will not be the same, will not tell you about the frequency error. And the actual reason is the frequency error is, if the frequency error is large, you will span this whole stuff, and the average value gives you 0. Okay. So, that is the thing. So, what we are looking here is there a block which can give me the correct frequency error value, okay, so that I can use it in the, I can detect the frequency error and correct for it as soon as possible. Okay. So, we have a block called as phase frequency detector, phase frequency detector. We will see what it does, which the other blocks were not doing. It is abbreviated as PFT. Okay. It is made up of, typically made up of 2 D flip flops. You can always design it at using some other digital circuit also, but you will see that okay, it can simply be designed using 2 D flip flops. Okay. The input D of both the flip flops are connected to VDD, the supply voltage. Okay. The Q of both the flip flops act as outputs for the PFT, and one of these is clocked by R signal, other is clocked by V signal, and these two signals, the Q of the two Q signals are actually used to reset the 2 flip flops using an AND gate. Okay. So, you have a reset here, I will just write reset here, and these 2 signals are called as up and down signals. Okay. You are a little bit familiar with up and down signals from the SR base PD. So, let us look at the operation of this. So, I have my R signal like this. First, look at the phase error detector operation. I have my R signal like this, and my V signal slightly shifted from here, just to show you how it will detect the phase error. In this case, right now I am assuming that the phase error, the frequencies are the same and the phase error is different. We will look for the frequency error in a moment. Okay. So, do not worry about that part. Okay. So, this is R signal, this is V signal. Assume that before t equal to 0, all the outputs were actually 0. Okay. So, what happens when you get your rising edge on R? What happens is that your up signal goes high. Okay. The down remains slow, there is no change in the down signal. Okay. Then when you get a rising edge on V, so rising edge on R signal makes my up signal go high, rising edge on V actually this triggers a rising edge on down signal. So, there will be a rising edge on down signal. Now, as you see, up was already high and down also goes high. So, these both the inputs of the AND gate, they are high now. Because they both are high, the reset signal goes high. So, as soon as your up and down signal, both the signals go high, your reset signal goes high, and if reset signal goes high, then you can say that both up and down will be brought to 0. So, there is some, in a real circuit, there is some time lag from down signal going high to reset signal going high, and then reset signal going high to up and down signal going low. So, right now I am just putting all of that time duration as reset signal going low. So, within this time you can see that okay, your down signal will go low, and your up signal will also go low. Right now this particular delay is very small, just you can just neglect it. I deliberately did not make this as that okay, down remains slow and up also comes slow. So, one exaggeration for this can be, I will show you on the other edge that my up signal goes high here, okay, and as soon as I get my rising edge on the V signal, my down signal remains low and up signal also comes low. This is the exaggeration that your as soon as you get your rising edge on V, your up signal down signal goes high and down, as because the down signal goes high and down up was already high. So, up and down will both make reset go high and reset will reset the reset signal will reset the outputs of the two D flip flops. So, actually your up will come down. Okay. So, this is like everything happens at the same instant. Here I am showing that there is some kind of delay associated with it, but and the actual phase error information is in this part only, right. So, now you look at up minus down is high only during the time of the phase error. So, this is delta. So, if I want to write the average of the PFT output, so V PFT here average is equal to up minus down average. Okay. If the amplitude which I am using for my voltage happens to be A, just an amplitude, then it is going to be A into, you know, up is high only for delta t time and this divided by t, the time period of the reference clock, which is equal to A by 2 pi into phase error. If A happens to be 1, then you can say V PFT output average is 1 by 2 pi times phase error. Okay. What happens if the phase error is negative? Well, let us just make some change here. Okay. Let us say your V signal goes high, then in this particular case your down signal will go high first, okay, and your up signal will already be low and that will remain low and down signal will go low as soon as your up signal goes, as soon as your R signal goes high. So, this your rising edge on V triggers the down signal and rising edge on R triggers up signal, making it to go low. Okay. So, here on both the sides, if you are having this delta t, then for this particular error you will get average value as negative, right. So, the phase error detector characteristics, if you look at, okay, this is phase error and this happens to be your VPFT average. So, from minus 2 pi to 2 pi, it is a straight line. Okay, this is 2 pi, this is minus 2 pi. The gain in our case with amplitude 1 is happens to be 1 over 2 pi. Okay. So, this is the first phase error detector where you see it is linear across the 0 phase error, right. So, I can very well call as a phase error detector, the linear range is minus 2 pi to 2 pi for phase error and the gain KPD happens to be 1 over 2 pi volt per radians. Right. Now, what happens when the phase error is more than 2 pi with respect to your reference clock, right. If it happens to be that the phase error is greater than 2 pi, you will find that it will always go like this. Okay. How? Let us just look at it. So, this for an example, let us consider that your reference clock period is, this is your reference clock period for example, you can choose either way. Okay. Fine, and my, this is my R signal and my V signal happens to be, let us say start at the same point, but this happens to be something like this. So, here I am taking this as 1.75. So, I should make it like this. Let us do it this way. Okay. So, yeah. This is just an example which I am having, right. So, in this case what you see is initially you see both up and down R and V both you get the rising edge at the same time, then up signal and down signal. So, what is going to happen when you get your rising edge? So, first when you have rising edge on R and rising edge on V both, you can think ideally both the flip flops output will go to 1 and then they will both go to 0 because the reset will get active. Okay. Both are going to be like that. Then as soon as you get a rising edge on R, you increase, this goes high. Okay. And you do not have a rising edge on V yet. So, your up will be maintained, down will keep 0. Then you get another rising edge on R. Well, even if you get another rising edge on the R, it does not make any difference. Your up still remains high. You get another rising edge, still remains high, and then you get a rising edge on V. So, when you get the rising edge on V, what happens? Your up will go down. And then at the very next rising edge on R, you again increase this, right. And then at this particular point, it depends whether they both come at the same time, or if your term V signal is slightly before your rising edge on up signal, then it will go down. So, here if you think about it, right, the phase error which you are measuring at any given instant of time, for phase error, one thing is we are measuring the phase error with respect to the reference clock period. So, as I told you, you are always measuring the phase error with respect to the reference clock period. Okay. So, in first reference clock period, you see that the error is 0, right, because they both are aligned. And then if you look at the second rising edge on R, with respect to the second rising edge on R, in this whole period, you do not find a rising edge of V. Okay. So, your error between the two rising edges, if I look at it, between the two rising edges, when you get this one and when you get here, this is like 2.5 clock period at TV. This is your error. What this is my phase error. So, up minus down signal, if you just think about it, up minus down signal, the average value here for this clock cycle, up minus down, it remains 1, it still remains 1 during the next, and then it goes to 1, and then after that it goes to 0. So, the phase error between these two signals, where you actually see the frequency error, the phase error is actually larger than 2 pi. Larger than 2 pi phase error here means larger than T period. Okay. but the average value of up minus down is high for a longer time, but if you look at the average value for each period, it is no more greater than the maximum value which you have from this PFT. Okay. So, your frequency error is large, your phase error is as shown here, your average value of PFT output is still limited between -1 to 1, depending on you have a positive frequency error or negative frequency error. So, in this particular case, your FR is larger than FV. Okay. So, you can say your reference accumulates phase faster than your V signal. So, here you will see that if you start from here, you will start changing your average value. If you are looking for the average value of VPFD at every clock cycle, it will keep on increasing depending on what frequency error do you have, and then it will at one point it will reset, and then again it will keep on increasing. So, this happens to be in a periodic manner. The nice thing about this is that if the frequency error is positive, it will always remain positive. If the frequency error is negative, it will always remain negative. Okay. So, for a positive frequency error, when your phase error is increasing in one direction itself, the average value of the phase detector output is not equal to 0, unlike the previous case. Here the phase error will keep on increasing in one direction, and then the average value of VPD average value of phase detector output will be equal to 0. That does not happen here. Okay. So, this is this is useful for us to employ this as a PFT, and do not worry about it whether the phase detector will detect the frequency error in the given time and correct, and the PLL will lock. Well, those problems do not arise here. Okay. So, here what you see is you employ this PFT in your PLL loop, it will actually detect the frequency error and increase the frequency in the correct direction always, change the frequency in the correct direction always. Okay. So, that is about the phase frequency detector. Now, you may ask me the transfer function as a frequency detector. So, what I have shown you as a average of the PFT output. Now, if I just want to use it as a frequency detector, well, you can use it simply as a frequency detector, and then it has frequency transfer characteristics. Let me just write, well, it comes after some good amount of maths. So, I will skip the maths here. I will just show you what kind of frequency transfer characteristics the PFT has. Okay. So, the average value of up minus down is equal to 1 minus 0.5 times FV by FR if FR is greater than FV, and the other one is 0.5 times FR by FV minus 1 if FV is greater than FR. One thing is, you will see that it is not symmetric around the frequency error 0. Well, that is fine, at least it is detecting the correct sign of the frequency error, that is more important. So, if I just plot this, what you will see is when there is no frequency error, right, the value is actually 0.5. So, what I am plotting here is V of up minus down average with respect to the frequency, the FV here. Okay. So, FR is the reference which is fixed, and this particular value happens to be asymptotically it reaches to minus 1. Okay. At this node you have Fr equal to Fv. Okay. So, well, these transfer characteristic you may not use it in your PLL. The only thing which it is telling you is that if I use this PFT, I will detect the sign of the frequency error correctly. I will apply the correct change to the VCO's frequency all the time, and I will acquire the frequency locking also. Okay.